Okay, welcome to the third class meeting of EC 202, Introduction to Probability and Random Processes. Last time we started to cover chapter 1 entitled Probability, and we covered a little bit up to this point. So let's quickly review the important terminologies we covered, and then let's dive into the probability measure. So as you see, I have been helped by Gemini to upgrade the handout. So this is the famous problem of Plato and Socrates. And I heard that this problem is also studied by philosophers. Of course, the Plato and Socrates are kind of fathers of the philosophy. And of course, the mathematicians or just the smart guys formulated the problem, and it is called sometimes secretary problem or best price problem, as you see here. Let me use this. Yeah. And I'm not going to cover how to prove it and what is the exact derivation when capital N, the number of candidates are sufficiently large. But as I told you, that magical 1 over E appears again and again. So just remember, this is very interesting. And it may give you a kind of baseline in making a choice when you have a dilemma, okay? And the next Bewley says that why do we need, as electrical engineers, this probability theory? And the key word is uncertainty. So we have uncertainty in electrical systems, even computer networks. So in order to mathematically handle, we study this probability theory based random variables and processes. Of course, as I told you, we may use strict inequality to combat with uncertainty. Sometimes, never forget, sometimes probability theory becomes useless. You will find that kind of situation because you cannot mathematically model your uncertainty. In that case, the safest way is just to use strict inequality. That may save you in your financial bankrupt. And as probably some of you already know that yesterday and today, our stock market Kospi has the historical downfall. And in that case, some statistical model-based risk management system may fail. And you may lose all the lifetime savings. In that case, try not to rely on probability theory. Got it? I told you, don't blame me after you lose all the lifetime savings. Anyway, so we are going to eventually learn so-called random processes. Why? Because in electrical system, we basically model electrical signal, not as scalars, not as sometimes vectors, but as continuous time signals with uncertainty, or discrete time signal, which is mathematically a sequence with uncertainty. So this is our goal, random process. That's why our title of this course is probability and everything dropped and random processes. But up until we meet the concept of random processes, we will study random variables, random vectors, and random sequences. Okay. And what else? Okay. So here comes the most important terminology. Some of you are familiar with, but most of you are not. That is the random experiment. So random experiment is different from ordinary experiment, where we may have outcome totally deterministic. Random experiment has outcome that has uncertainty. And Whenever we perform this random experiment, that is called trial, and the result is called outcome. So we may have a block diagram because electrical engineers really love block diagrams. So we have here some source that generates an outcome, and this block may be named as a random experiment, and you're pushing it or hitting the box, maybe a trial, and you have an outcome. Got it? And what is an event? Event is a subset of the set of all possible outcomes. So sometimes when you roll a die, outcome is a single number among 1 through 6, but you may have interest in finding the probability of S is even. In that case, S equals 2, 4, or 6. So this is event. Got it? And what is probability? Probability is now in this course and forever from now on will be viewed as a function. But what kind of function? Whenever you have a function, then you have a name and just a second. Okay, you have a domain, and how do you read it? By the way, this is into. Got it? So function p from D to some. This is codomain, and this is domain. Got it? So we view the probability measure or probability law as a function. But what is the domain in this case? In order to mathematically precisely discuss this function, we view our event as a set. So this one will have sets, especially subsets of the sample space, the set of all possible outcomes. And then what will be this one? You may say it's a real number, but more compactly, it's an interval from 0 to 1. Anyway, so here goes the review of set theoretical terminologies. I will skip all of them. And here goes the another set of terminologies where I wanted you to remember some interesting function called indicator function that is named as numeric 1, but it has subscript where you put a set from your implied universal set, and here goes the argument of the function. And the value is either 1 or 0. And what else? Subset, mutually exclusive. And here goes another one. So when you want to define set of sets, which is very, very dangerous definition. So we don't want to say set of sets. We usually say group of sets or collection of sets. And one interesting class of sets is the power set of a set. And I explained why we have this strange notation, because when S has cardinality, which is the number of elements denoted by this one, then 2 to the S has what? This many elements. Got it? So we have this strange notation. And what else? We wanted to use visualization methods like Venn diagram, but as I told you, precisely speaking, we call Venn diagram are not Venn diagrams. Some mathematician told me, actually, what we call a Venn diagram is an Euler diagram, but I don't know what's the difference anyway. And the difference between high school math and college level or university level math or math-related courses should be what? You now have distinction between two infinities. One is countable infinity, and the other is uncountable infinity. And this is very, very, very important. So if you have any doubt, ask your friendly Gemini, and or me. Probably I will open Gemini and ask. Okay. Anyway, and also I mentioned the meaning of infinity for engineers. In many cases, infinity is just to make our mathematical justification precise whenever we want to handle sufficiently large something, sufficiently small something, but we don't know what is the exact number. So in that case, we use the mathematical formula like this and justify our approximate value, probably the limit, is well justified for sufficiently large t. So this means for sufficiently large t. That is the engineering meaning of limit t tends to infinity. By the way, some of you have already noticed that whenever I define something, I want to check the existence and uniqueness of what I just defined. And while I was talking about this, I boldly said that there are some Northeastern Asia languages are inferior in the sense that we have no article, the, or strict plurality, or sometimes we even do not have gender of the word. And some of you learned, for example, French, the French language, or Espanol, and you've seen some strange things. Ship is female and something is male. But that actually makes a lot of confusion just disappear whenever we write very academic article. Got it? So you will see, for example, as I wrote here, I really love mixing Korean with English words. And if it is necessary, I try to put S, quizzes, you see, exams, and sometimes even I put articles, or something like that. And some of my relatives last month told me that this time of LLM, even we don't need to learn English, but that's very, very long. As I told you, if we translate some French written or English written academic article into Korean, then a lot of information just disappear. And you have to go back to the original manuscript. Otherwise, you have confusion persisting forever. So study English, at least very hard. So here goes another thing entitled set operations. And what kind of operations have you seen in elementary algebra? In elementary algebra, we learned addition, subtraction, multiplication, and division, right? And division was a monster because when you are a lower grade, then after division, you have quotient and remainder. And suddenly, after we introduced the rational number, 2 divided by 3 is 2/3, and everybody just got shocked, something like that. But anyway, interesting thing is that we have something very similar to elementary algebra operations. And that is what? Complementation and set intersection and union. And as you learned in logical circuit, these 3 operations are just foundation of computer, modern computer. And sometimes we want XOR or symmetric difference. Then these 3 things can be just combined. How many? Sometimes finite times, sometimes countably, infinite times, infinite set operations we consider. Got it? Most of the circuits, because of the limitation, we may perform finite set operations, finite number of set operations, but mathematically, and especially in this course for probability, you will see countably infinite set operations are allowed in many cases. Uncountable infinity, that is a subtle thing, and if you have interest, then enjoy that exploration with your friendly Gemini, or you take more advanced course. As I told you, I do not want to spend too much time to proving something, okay? I will try to make this course as engineering course as possible. Of course, you don't agree in the end. Anyway, here goes complement, union, and intersection, and other derived, derived set operations. You all know. And here goes some interesting things like countable union and finite union and finite intersection, and countable union and countable intersection. And eventually you may have some uncountable union and uncountable intersection, but this will rarely appear in this course. And also, as I emphasize that even though I will not ask you to solve some real analysis type problem in this course, but just remember, as you had sequence of real numbers and considered the limit of this sequence, we have a sequence of subsets of some universal set, and we also consider the limit of the set sequence. And this is very necessary for advanced probability course. And of course, you just stopped here in your high school, but as you learned in some elementary, little bit not elementary calculus, we introduce not only sup and inf, but also lim sup and lim inf. Similarly, here we have almost the same thing, but the difference is that countable intersection, countable union replaces sup and inf, but still we have lim sup of a sequence of subsets and lim inf of a subset of a sequence. So something like this. Got it? So don't be frustrated. I'm just introducing your new guys and saying that, hey, just know his or her name. Got it? And someday, some of you, when you do your graduate level research, you may need these concepts of lim sup of a sequence of subsets, but mostly not. Got it? Anyway, so we now have arrived section 1.4, and last time we covered a little bit of this section. And we want to make a previous discussion about the modeling a random experiment using set theory, more precise in this section. So first thing is so-called the probability space. And probability space is a triplet. What is a triplet? Triplet means one thing that consists of three things. So here, this parenthesis gives one thing, and we have three things. This is sample space, and actually these two pair is called event space, and this is called probability measure, or sometimes probability law, or if you want, probability function. And just for convenience, many undergraduate textbooks white lie, saying that E is the event space. But precisely speaking, this pair is an event space. And this is what? This should be a sigma algebra of subsets of S. And I'm not going to talk too much about sigma algebra because this is an introductory course. Anyway, the trouble with this sigma algebra is that if S, the sample space, is countable or finite, then you may just assume that we don't need some strange sigma algebra. Just the power set of the sample space is enough, as you all know from high school math. The problem is that from now on, you just remember, okay? As you just memorized many scientific results without proving in your high school science courses, saying that when the sample space is an uncountable set, then power set 2 to the s may be sometimes too big. So some subsets of the power set cannot be measurable. You cannot find the probability of that event. And people have found that makes a lot of trouble when we make everything precise mathematically. So Kolmogorov proposed not to use power set, just use a sigma algebra of subsets of the sample space. So, by the way, at the end of last class meeting, one of you asked me about the sigma algebra, and I told you this episode. When I was at your grade, there were 3 courses, 3 courses for the same probability and random processes. And one of the course, the professor was asked from a student about, hey, professor, I just don't understand what's the sigma algebra thing. And he started to show off his mathematical capability, and that was up to the end of the semester. So the class even couldn't reach random vector. I was not in that class, but in other class, we covered up to matched filter. And professor just showed his bag and write down everything. At that time, we didn't have projector like this, and even we didn't have OneNote. Anyway, so what we are going to do is that in order to mathematically model a random experiment, we are going to use a sample space. And a sample space consists of the probability space, a probability space, and it consists of these 3 things. Got it? And for now, you may just assume that this sample space is a set of all possible outcomes of your random experiment of interest. So if you toss a coin, heads and tails are in the sample space. If you roll a die, then the number 1 through 6 is in the sample space. So sample space is very simple. And as you see that, given a random experiment, by definition, right, if the random experiment is defined well, then sample space just exists. And it's, in many cases, obvious, and also it's unique. The trouble is that different random experiments, so suppose you have a fair coin, and you have a bent coin, then you may have same sample space. So different random experiments, of course, may have the same sample space. Since this sample space is finite set, the power set of this sample space can well serve as the sigma algebra. In that case, what distinguishes these 2 random experiments? The probability measure. So, for example, this is S fair, this is S biased, then 2 to the S fair may serve well as the sigma algebra for fair coin tossing. And you may call like this, but what's the difference? So for this event of heads, you may have 1/2, but here the different probability measure may have 1/3 and 2/3. Got it? For the heads and tails. So different random experiments may share the same sample space and event space, but they may have different probability measure. Got it? And depending on whether the sample space is a countable set or an uncountable set, we call the sample space as discrete and continuous. This is a little bit similar to our signal-gen systems terminology, like discrete time signal and continuous time signal, where discrete time usually means every possible time instance mapped to an integer, which is a set of countable infinite number of elements. And continuous time means t is a member of the real line and the set is uncountable. So very similar. And the event space, not this one, precisely speaking, this is the event space. And we have a lot of trouble, but for finite or countable, this power set is enough for the sigma algebra. But as I told you, you need what? You need really a sigma algebra of subsets of the sample space to make your mathematics precise. By the way, why the set, a class of sets, is called algebra or field? Because we allow set algebraic operations with the elements of this thing, and we want the countable set operations must be in that class of the subsets. So here, the key is that we want closedness under countable operations, countable set operations. We may have countably infinite set operations, but still we want the result be a member of this class collection. Got it? Anyway, so where is the example? I remember I've given you. Okay, here. So even though in die rolling experiment, you may say that the power set with this sample space is enough to mathematically model a rolling die experiment. But some people may say that, hey, I'm only interested in these events. And let me choose this sigma algebra of subsets of S. And you should not say that, hey, you are wrong. Never say that. He or she is still correct as far as the person is interested in what? Countable set operations on these 4 events. Got it? Anyway, what else? Let me just skip this, okay? But here, interesting thing comes. There is a sigma algebra called the Borel sigma algebra or Borel sigma field, and there are many types with this superscript or exponent. So B and B2, of course, B3 and B anything like this. And they are all related with what? The set of real numbers, the set of a pair of the set of pairs of real numbers. So they are all related. And what should be the Borel sigma algebra? Borel sigma algebra, as it says, is a sigma algebra of subsets of real numbers. The Borel sigma field B to the n is a sigma algebra of subsets of, R to the n. And interestingly, these Borel sigma algebra are so-called generated. This is a terminology I'm not defining, but it's generated by these half intervals. And many of you already noticed that, okay, that interval appeared when I computed the cumulative distribution function. That's it. Actually, that's why we defined CDFs, not just PDFs. Anyway, same thing, and you will see, actually, you will see these 2 things again when we learn random variables and random vectors. Got it? Anyway, now the review is over and we are now studying this probability measure. So we are going to talk about the third component of a probability space that is called the probability law or the probability function or the probability measure of the probability space. And as I told you, we have what? The domain and the codomain. And here, the domain E must be a sigma algebra of subsets of the sample space. We already restrict E as a sigma algebra. What does that mean? As a class, this sigma algebra has a lot of events as its members. And whatever countable set operation we perform on these subsets, still our result must be in that class. So we have assumed closedness under countable set operations. Then Kolmogorov just provided only 3 axioms. And many textbooks, especially undergraduate level textbook, has more than 3. And even I got confused. I got confused when I saw it because one textbook says 4 axioms, the other says 5. But eventually, when I took the graduate level probability course, I noticed that since we already assume that class E is a sigma algebra, actually, these 3 axioms are enough. We don't need more axioms. All the other axioms can be derived from this one. Got it? Anyway, by the way, each axiom has its name because they are so important. And especially this third one has its famous name, and that is called countable additivity. Why it is called countable additivity? See that? The right side of this equation has how many terms for that summation? How many terms? Countably infinite, right? As you see, the lower limit is 1 and the upper limit is infinity. And what does that mean? Actually, you substitute I with every natural number. So you have countably infinite terms to be added. That's why it is called countable additivity. However, we need this important restriction. For these events, they must have no intersection or intersection of any ith event and jth event with I not equal to j must be what? The empty set. This is called pairwise disjoint or mutually exclusiveness. Got it? And as you learned already in your elementary school or middle school or high school math, let's take a look at this Venn diagram and just to see that this area represents the probability of each event. In that case, we know that since A intersection B is the empty set, what do we have? The probability of union of these 2 events is simply the sum of probabilities, right? And you already know that if they have non-zero area intersected, then we need one more term. And this is generalized for how many? This is 2, then 3, 4, and countable infinity. Got it? So the third axiom, or you may say assumption, led us to handle infinite something in probability theory. And many of you wonder why we don't have uncountable additivity. And that's a very good question. And you will see, not today, when we study continuous random variables, then we will come to this problem again. Okay. So anyway, countable additivity. It's not uncountable additivity. This is the key. And last time, I also emphasized, continuity of the probability measures. So whenever we model a random experiment using a probability space where we have a probability measure, then the probability measure as a set function is always continuous. You don't need to prove it as an electrical engineer. Got it? So you may say that, right? It's just Gemini, please find some very popular, rigorous book proving continuity of probability measure. And then in your thesis, just to say that the Billingsley's book, chapter something, has the proof. Then we are done. Got it? We are not mathematicians, fortunately. Got it? So this is exactly the extension of continuity of a real function when you handled during the high school. Anyway, by the way, here goes very important word, terminology in mathematics related engineering. So characterize, what is a character? Character is 특성 or something. So whenever we have characteristic or characterization in math related courses, then we put the Korean word 특성. For example, characteristic polynomial, 특성 방정식, right? Something like that. And what does that precisely mean? Characterization means that we have full description. So we fully describe something. In that case, we put the terminal, the word character or characterization or characteristic. So if you see a homework problem or exam problem, how many ways to characterize a random variable have you seen in this course? Something like that. And then you must answer like blah, 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 blah. And you know what does that mean by characterize a random variable. Now let's have an application. So today and in the last class meeting, how do you model a random experiment? How do you characterize a random experiment? You may say that I characterize a random experiment using a probability space. Got it? Got it? Anyway, for the sample space, countable sample space, then just having probability of singleton event. As far as you know the probabilities of every singleton events, then you are done. And it's kind of intuitive. I'm not going to explain it. Got it? However, for continuous sample space, we have a big problem. That's why we learn all these things. And actually, we learned in our high school math, even if you didn't learn, when I was a high school student, we had the last chapter of 수학의 정석 talking about probability and statistics, where we had 확률 밀도함수, 누적 확률 분포함수, everything. So here you go. The difference is that we also study probability mass function, which is you already know, but we also study so-called the characteristic function. And as name hints, the characteristic function of a random variable really characterizes the random variable. That's why it is named a characteristic function. Anyway. By the way, all these things, you just read it. They are very easy. It's like just reading 수학의 정석 several times. Okay? So I'm not going to cover them all. By the way, the third axiom required pairwise exclusiveness. But what if we remove that disjointness? Then, as you already know from this simple Venn diagram, probability of A union B and probability of A plus probability of B, which one is greater? That one, right? By the way, this is for two events. for general n and countably infinite events, you have what? This is, by the way, n can be infinity. Got it? This is called self-additivity, kind of inferior version of countable additivity. And this right side or right-hand side is called the union bound. Union is bounded by this number. Probability of union is upper bounded by sum of the probabilities. That is called union bound. And also about the inclusion-exclusion principle, you may prove using mathematical induction, but you may use indicator function as I introduced here, and using that idea, very, very interesting. By the way, here goes the so-called frequentist perspective and the Bayesian perspective about the probability. And the statisticians, not every statisticians, but many statisticians interpret probability as a kind of ratio of two numbers in their data set. Got it? And Bayesian perspective, you interpret probability as your belief on some event. And the major difference occurs this. What if you can only have single trial for your specific random experiment? The trouble of frequentist is that, well, is it a good idea to talk about probability when you can only try something? But in Bayesian perspective, that's okay. Anyway, probability means just a number, ranges from 0 to 1 to reflect your belief. And probability theory actually systematically allows you to compute the belief given a lot of information. So this Bayesian approach is very, very interesting and prevalent, especially in our modern artificial intelligence, especially for training a neural network and performing task, let the network perform a task. In that case, actually, we highly rely on this Bayesian perspective. Both of the perspectives, but mathematically abstracted, still they want what? They use probability space to model a random experiment and all the theories we study here. The problem is that as an engineer, which one do we prefer? Actually, we mix both of them. And you will see, not in AI or ML course, but in so-called statistical inference course. Of course, graduate level, statistical inference is called statistical signal processing. Then you will see, actually, there are two types of unknown something. So as I told you, inequality is a good choice to confront uncertainty. But sometimes, whenever we have something unknown, then we just say that unknown, not random. Unknown, random. Two approaches we have. So be careful, be careful. Even though I teach you probability theory where our uncertain real number is modeled as a random variable, there are many engineering problems. You just view that number as something unknown. Got it? Not probabilistically modeled. Anyway, yeah, just read it. You can read. Okay, here goes the notion of joint and conditional probabilities. We all learned actually in our high school math, just we learned the terminologies in English. So suppose we have two events, A and B, And when we compute the probability of the event A intersection B, this probability is, of course, probability of the event represented as the intersection, but sometimes we just call this is a joint probability of the event A and B. Got it? So and means intersection. And yeah, just a second. Yeah, we will be back with this mosaic plot. Just a second. Yeah. So here we have. Now we learn the important notion of a partition. What is a partition? Suppose you have a dish and you broke it into 3 pieces. Then, of course, this union is not the original dish. It's broken dish, but anyway. And what else? So whenever you have a subset of, in our case, sample space, subsets of sample spaces, and union of all of them becomes the sample space, and they are pairwise disjoint, then this class of subsets is called a partition of S. Of course, you may have some subset of the sample space and may consider a partition of the event A. In that case, those members of the partition are, of course, mutually disjoint or exclusive, but the union of them becomes the event A. In that case, that class of subsets is called a partition of S. Got it? Now, here, let's consider 2 partitions of the sample spaces given a random experiment. And one is, in this case, A1, A2. So you have 2 events, A1, A2, and also B1, B2. And of course, A1 intersection A2 is the empty set, and A1 union A2 equals the sample space. And here, B1, B2, mutually exclusive, and they become the sample space. So what is an example? When you roll off die, A1 is what? The event of the outcome is an even number. What is A2? Odd number. What is B1? 1, 2, 3. B2? 4, 5, 6. Something like that. Got it? So you have 2 partitions of the sample space. Then this plot is called, of course, these 2 are called mosaic plots. Probably some of you, when you study the probability and statistics, you've seen this one in your textbook. I really love it because it provides visualization of what we know. And the difference between the left side and right side is which partition you prefer. So in the left side, you prefer partition A1, A2. So what you do is that you draw a square with length of each side unity. So this is 1, okay? The length is 1, and that is 1. And suppose this is 0.3 and 0.7, then what you do is that you divide this length one side into 0.3 and 0.7. And then you draw a line. Got it? And then what do? You find this length. How? By computing the probability of this joint event. And then this length times that length must be the probability of the joint event. This is the way to draw a mosaic plot. And here in this mosaic plot, we are more interested in the partition B1, B2. So we divide this vertical side with length, for example, 0.4 and 0.6. And then we do the same thing. So as you see here, what is the summation of all these 4 joint events? Should be 1, right? And you may say that, hey, it's obvious, but you will see that your conditional probability formula and your total probability formula and your Bayes theorem formula is very well explained using this mosaic plot. So even though today I may not go up to that topic, just remember what I just told you and try to, of course, also remember what you learned in your high school probability or undergraduate elementary probability and statistics about the total probability theorem, conditional probability, and Bayes theorem, and try to use this mosaic plot and try to interpret the result. By the way, your handout has a beautiful URL. Somewhere I put it. So if you click that, you will see a very well-made YouTube lecture, not me, explaining the conditional probability and total probability theorem and Bayes theorem using this mosaic plot. Anyway, why do I introduce this one even though it's not that important in this course? Because of the power of visualization. In the first class meeting, I've shown you a blog of your senior, or how to say it, 선배 of electrical engineering. And he really followed my advice. And he says that his success as an electrical engineer just stemmed from practicing these 2 principles whenever he want to make a presentation or want to solve some engineering problem. So never forget. Ready? So whenever you have good visualization tool, try to use it and get acquainted with it. Sometimes you may forget all of the results I tell you, but you may still remember these plots, these mosaic plots, to still remember all the important theorems in probability theory. Now, here goes the conditional probability, and you all believe you know this. I also believed that when I was at your position, but you are not, okay? And I was not knowing that. Here goes the idea of conditional probability. Many of you, and some of you are baseball fans, right? And in baseball, that will be our regular season will open in a month. I really a fan of Lotte Giants, and I really still remember our team win the Korean Series in 1984 and 1992. Is it? Yeah, and lost the Korean Series in 1995 and 1999. And whenever I watch a baseball broadcast, the caster says that, okay, next batter is Han Dong-hee and his batting average is something. And the commentator says that, no, that's not the statistics you need to see. Han Dong-hee is very weak for the underhand thrower, something like that. And given underhand thrower, Han Dong-hee's batting rate is plummeting, something like that. And then there is the opponent team's coach putting new pitcher underhand. That is precisely the meaning of conditional probability, as you know. Got it? So we have our intuition whenever we think about conditional probability and even total probability. Let me just introduce another idea. Suppose Han Dong-hee has betting average given left-handed pitcher is something and right-handed pitcher is something. Then what is the average, betting average? You all know that you multiply of course, actually, we here all need Han Dong-hee, but anyway, we add up to have the betting average. Actually, this is what? This is nothing but the total probability theorem. So this is a good model. And whenever we have a very good model to understand some concepts, we call that model as a mental model. So this baseball betting average may serve as a good mental model to understand the conditional probability and total probability. And also this using mosaic plot to represent the joint probabilities given two partitions of the sample space may be a good mental model. Right? Anyway, so let's see. Very important thing. You know that the conditional probability of what? See that? You must read this one as the conditional probability of the event A given B. Or I more prefer probability of A, right? Just the P of A, probability of event A conditioned on the event B. Right? There are many ways to read it, but I prefer reading this as probability of A, probability of the event A conditioned on the event B. And we defined this term like this. As you all know, actually, this appeared in our high school math textbook. But the question is, why? Why we define this one as conditional probability? Actually, the reason is that it's intuitive from our intuition. So consider Han Dong-hee's betting average for the left-handed pitcher. What do? You, from your record about Han Dong-hee's every batters on, you find only the lines when he confronted left-handed. And then you, given that, and also you find what? Left-handed hit. And you count the numbers and you divide them to have what? The conditional betting average. That's why we have this definition. Right? So it's kind of obvious. The problem is that up to this point, we are no more than high school probability course. But let's a little bit have the undergraduate level flavor. So let me ask you, conditional probability is always well defined? Does it exist? Whenever you have a ratio, then you still remember your high school lesson. What? The denominator shouldn't be 0, right? So as you see, the event B, right, as a member of the sigma algebra must have positive probability. And you may say that, hey, it's obvious. It's not obvious. Actually, this will be extended for the random variable case, and you will see something very, very strange. We will put something 0 here. Actually, we are not, but it seems like we put something 0 in the denominator and claim something. So let me give you, okay, some of you just wonder what is that. So let me give you. So suppose random variable x is standard normal. Many of you already know this, right? The PDF is Gaussian, bell-shaped curve. You all know that actually, right? Now, what is the probability density function? Conditional probability density function of this normal random variable when the event x squared equals 1 is given. We know that, actually I didn't teach, but you know that this event has probability 0, right? But how can we define this one? And that is a kind of agro or spoiler. So you think about it, got it? So far, we are okay. We only handle the probability of events. So we just do not allow 0 appearing in the denominator. Now, about the uniqueness. Of course, this when we are given two events or from a single random experiment modeled by a probability space, this value is of course unique if we have described the random experiment precisely. The problem is that, what is this P, by the way? See that I just said PA given B, PA union B divided by PB. We know about this P. What is that? That is the probability measure we have to describe our random experiment. Then what is this one? This is a new notation. Got it? This PA given B is a new notation to mean this ratio of the probabilities in terms of our probability measure. Now you may say that, hey, actually this P is a function, a set function. What about this P? That's the difference between our high school probability and this graduate level thing. So what we do is that we define this P dot conditioning bar given event B as a new function. And this function has the domain same as the sigma algebra of our original probability space. See that? Got it? What does that mean? Here, P dot bar B is a function, even though it has strange notation. But you still remember this one, F domain into codomain, right? Same thing, just we have strange thing. If you really dislike that, let's call this as Q. So Q from E to the interval 0, 1. Now what is this one? As P was, now this Q is also a set function, right? So from now on, you no longer consider conditional probability as something divided by something other thing. You are now going to view the conditional probability as what? A set function. And its domain is same as your original probability measure. Got it? And you can actually show that after we rename this strange set function as Q, you can also show that three axioms that must be satisfied by any probability measure is also satisfied by this function Q when you define this function Q as what? Q as Q of something as what? As this one. So as I claimed, this conditional probability is actually a probability measure. So interesting thing just happened. What? We are given a random experiment. And we modeled it using a probability space. So far, how many probability measures do we have? One, the P, right? But now interesting thing happens. You choose an event, B, that is a member of the sigma algebra, which means that this is a new event. Now you define new function, new set function. Then what happens? Suddenly you have what? Another probability space. Now this new probability space has same sample space, same event space, and new probability measure. Now let me ask you, what if you choose a different event from B, from this E? Then you can construct another one, another one, another one. As many new probability spaces as possible, if you want. Got it? So interestingly, given just a single random experiment, which is described by a probability space, you may have many different probability spaces. And what are they? They are talking about probability of events. Still probability of events, but they are all different in the sense that they kind of shrink your interest into specific event. Got it? So this is the difference between your old idea of conditional probability and the idea in this course. By the way, whenever we have something defined as a ratio, it is very pedagogical, 교육적인, when you just multiply both sides with the same non-negative number. And here goes the idea. Recall this one. So you leave the numerator here and multiply these two. And now let me ask you, what about, so this is all about the probability measure P dot bar B, and this one is about another probability measure. And let's define naturally as this one. And you plug in B here, then what happens? You will see you have the same thing, but having the different shapes, right? And you may say that, hey, it's obvious, right? But something obvious may have different interpretations. So this single joint probability now can be factored or rewritten as a multiplication of two probabilities. And here, this is what? Unconditional probability, or just probability of event, and this is the conditional probability. And again, you have unconditional and conditional, but what? Using different probability measures. See that? This and that actually comes from the original probability measure. But here you use different probability measures. And two different probability measures are linked in this way. Another thing, probability of joint events A and B is the product of probability of event A and probability of event B, conditioned on the probability of event. So that's why I love reading this conditional probability as probability of event B conditioned on A. See that? Probability of A times probability of B conditioned on A, right? So interestingly, joint probability is the product of two probabilities. One unconditional, the other conditional. Got it? Now, you have n equals 2, then we may have n equals 3. And this is not that difficult. You just put parentheses and apply the case with 2 again and again, and you will have what? If we just select in this order, you have joint probability of A, B, and C events is probability of A times probability of B given A, and probability of C given A and B. Now, is this the only expression? No. As you learned in high school math, choosing the order from 3 things is what? 3 factorial. So actually, even though I didn't write, we have different 3 possible factorings. And interesting thing is this one. Given the same joint probability, you may have 6 different representations. Which one is better? It depends on your situation. One of them or some of them may be very, very useful for your problem. The others not. You have to have the idea which one to choose. Got it? And it's all up to you. Now, this case with 2 things may provide us a very interesting idea that is related to statistical inference. And it's like this. So this is what? This is probability of Han-Dong-Yi hitting an an타 given left-handed. And what? You have the Han-Dong-Yi's betting average. And as you see that, this formula updates the probability of hitting to probability of hitting conditioned on the left-handed by multiplying a correction factor. You can interpret it that way. Of course, this is a definition. And what is this one? By the way, this is the famous what? The conditional probability when you have difficulty in computing, you just switch these two. That is the idea in your high school math, right? Of course, this is also a very important interpretation of the conditional probability. Got it? So as I repeatedly tell you today, given the same mathematical thing, sometimes they have different interpretations. And you have to understand the interpretations of different expressions. Actually, even though they are the same, got it? And you may have sometimes sequential events. In that case, sometimes this one may be interpreted, not always interpreted as prior probability, and that is interpreted as posterior probability depending on the situation. And also you read it, and also you solve this one. It's not that difficult. And I believe I've covered up to here today. Got it? Okay, that's all for today.